This video is about matter waves. We learned earlier that electromagnetic radiation, that was initially thought to behave only as a wave, can, in some situations, behave as a particle. In 1924, the French physicist Louis de Broglie suggested that the opposite is also true, and that in some situations matter can also have wave-like properties. For example, electrons, that were initially discovered as particles, can, in some situations, behave as a wave. De Broglie added that the wavelength associated with a particle can be calculated using lambda is equal to h over p or h over m times v. In this equation, lambda is the de Broglie wavelength, h is Planck's constant, p is the momentum, and logically, m is the mass and v is the velocity of the particle. Note that the de Broglie wavelength formula is not provided in the IB Physics data booklet, but there is no need to memorize it, because it will be given to you if it comes up on an exam question. A year later, in 1925, Davison and Germer carried out an experiment that confirmed the de Broglie hypothesis. Here is a simple description of the experiment. A beam of electrons is passed through a crystal. If the electrons would behave as particles, they would only be slightly deviated by the atoms in the crystal, and as a result, we would get a single bright region at the center of the screen. However, this is not what happens. The electron beam is diffracted by the crystal through larger angles, and a diffraction pattern, so a series of bright and dark fringes, is formed on the screen behind the crystal. This is exactly the same type of interference pattern that is formed when light is diffracted through a diffraction grating. Since diffraction is a property of waves, electron diffraction is evidence that matter can have wave-like properties. This completes our discussion of matter waves. In the next video, we'll learn about pair production and pair annihilation.